Okay, good morning. So this is module 10, periodic motion, periodic motion part 1. So here we have a periodic motion or an oscillation defined as a motion that repeat themselves over and over. In this we have three examples like wave motion. Wave motion ni mo na naga-balik-balik lang siya. And you also have ang kaning orasan. It's just rotating. And you have the pendulum, which is going back and forth from one side to the other side. So a body that undergoes a periodic motion has a stable equilibrium position. Okay. So in this module, we're going to try to examine unsa ginadira sa periodic motion, unsa ang mga physics behind it, unsa ang mga quantities na ato ang bantayan. And you will notice that some of the quantities are familiar na ta. Okay, let's go. So here we have a spring. Spring attached to it is a mass, and it is attached also to a fixed position here. So here we have the equilibrium position. So it is here, it is unstretched. So ang force lang na diri is the normal force ug ang weight as shown here. Okay. So this is a frictionless nga track. And if it is compressed siya padulong here. So ang spring ni gamay, and it would have this Fx. Fx is like the force exerted by the spring. Sometimes we call it the restoring force. Iyang itry og restore body. So if you look at the free body diagram niya, you have the normal force, okay, now just surface, of course, na ang weight. But unlike sa katong first nga position na natay Fx or the restoring force niya, this is the reaction of the one. But actually, natin ignore diri, which is the force na pag-compress sa spring niya. Now, if we release it, if we release the object, the block of mass, it will exert force, Fx, and it will push the block of mass in the opposite direction as indicated by this one. So, pag mula pa siya sa equilibrium position and goes at maximum length niya such that ang velocity niya mo 0 here, iyan na po try og bira balik ang block of mass in the opposite direction. Ang goal is para mo reach sa katong equilibrium position niya. And we look at ang mga terms na nadiri. So x, when it is at maximum, let's say the velocity would be 0, is what we call the amplitude, denoted by A. Okay, this is amplitude is measured from its equilibrium state or at the origin towards the maximum na position niya. A cycle is also denotes a complete vibration or a complete round trip made up by the body that undergoes periodic motion, such as kaning pendulum. So starts here, goes here, and goes back. So nasa initial position, goes middle, then it goes beyond the middle, then nibalik na po din siya, ni-reverse na po the motion, then it goes back sa final position niya, which is the initial position. That's the complete, or that's one cycle. Okay, it simply goes back to its initial position. That's for a complete cycle, one cycle. Other terms is the period T. The period T is the time for one complete cycle. And you have the frequency. The frequency is the cycles per unit time, which is just 1 over the period. And ang units of frequency is denoted as hertz. 1 hertz is equal to 1 cycle per second, or simply 1 over s, or 1s to the negative 1. And we also have the angular frequency. I think we remember we also use this symbol, the angular velocity. So you have equal to 2 pi times f, which is also equal to 2 pi over t. So it's like a distance over the time, 2 pi t. So here we have the relationships of the frequency with respect to the period. Unit niya is hertz. Period and unit niya is in seconds. Okay, and you have the angular frequency or the angular velocity, if we learned, is just 2 pi, the distance for one complete cycle, times f, or 2 pi divided by the time t, or the period for one complete cycle. Let's go. Here we introduce the simple harmonic motion. The simple harmonic motion is simplest kind of oscillation that occurs when the restoring force Fx is directly proportional to the displacement from equilibrium. So Fx is equal to negative kx for a spring na situation. And this equation gives us the correct magnitude and sign of the force, whether x is positive, negative, or zero. Okay? So x is bali-bali siya kay posible siya on this side or on this side or at the equilibrium state. So a body that undergoes a simple harmonic motion is called a harmonic oscillator. So the force needed to stretch an ideal spring is proportional to its elongation, which is the stretched. Let's look at the acceleration for simple harmonic motion. For motions along a single axis, we recall the expression a is equal to d squared x dx squared. Okay, or this is the second derivative of the displacement x. Okay, remember our first derivative is v is equal to dx over dt. Second derivative gives you the acceleration. We also recall Newton's law of acceleration, which is mass times acceleration. And if we equate this to the expression negative kx, we can have this relationship. Okay, recall that the acceleration for simple harmonic motion is given by this expression, and if we equate this to, then we bring down ang imuhang mass to this side, so you get negative k over m. Okay, k over mx. Okay, so that is the expression for your acceleration. So we see that the negative sign here, that the acceleration and the displacement always have opposite direction. Okay, ang iyahang acceleration. Here we have a demonstration of duha ka type of motion. You have the rotation of motion and you have the linear motion here. So as it rotates repeatedly, ang iyang motion on the screen of this block or of this mass simply goes forward and backward with respect to this axis. Point P will oscillate back and forth. This point P here, back and forth in the screen as the ball rotates and this goes. So sa rotation mo you can get the angular velocity. Og na kay kanang mga amplitudes, you have the positive amplitude, the maximum at this point, and the negative amplitude at this point. So napud kay linear motion or rotational motion. Now let's look at the relationship between the linear and the circular simple harmonic motion. Okay. Here we have the mass, the point P and Q. So the OQ is a vector with reference from this line here. Reference point is an origin. Makes an angle phi with a positive x-axis. Okay, this positive x-axis. As the point Q moves around the reference circle with constant angular speed omega, the vector OQ rotates. This vector OQ rotates with the same angular speed. Such rotating vector, kaning OQ, is called a phasor. So the x component of the phasor, this one, the x component niya, is given as x is equal to a cosine phi. Kani siya nga vector. Okay. Where x is at the maximum amplitude a, and where x is equal to a as the maximum value of phi, is 0. Okay, 0 degrees. Now let's compare ang kaning duha ka event, actually the same event but different mga calculations. So ang imong position is given by x is equal to a cosine phi. If you take the first derivative of this one, this becomes dx over dt, gives you the velocity vx. And here, cosine phi dili man, so that means this becomes dA over dt. This becomes negative vq. So this is the vx, kanisha is equal to negative vq sine phi. But vq is the tangential velocity. So vx is equal to negative v tangential sine phi. Okay, negative siya because the derivative of a cosine is a negative sine. Negative sine. Now we look at the second figure. So the second figure, you now have the AQ in terms of acceleration. AQ is the radial acceleration and it is pointed towards the center of the origin. You still have some identical things, like for example, phi is still the same as phi here. So this is also phi. Now in terms of acceleration, we take the first derivative of the vx. So this becomes dvx dt, d quantity over dt. So okay, so dvx dt gives you ax, dv tangential na siya, over dt gives you a tangential. Oh no, a radial. Okay, this gives you the derivative of the v tangential, gives you the acceleration radial. And of course, the derivative of a sine is a cosine. Negative man siya daan, so we keep that. So this is the expression, and ax, the acceleration ax, is equal to the negative a radial cosine v. So let's go. Okay, so what do we do here? So we look at the expressions x, the position x is equal to a cosine phi, and ax is equal to the negative a radial, this one, this is a radial cosine phi, and we know that a radial, if you remember ang circular motion, is equal to omega squared times r. Now at maximum, r is the amplitude a, the rate. Okay. So then ax, substituting ax ni Muha is equal to omega squared a, and what is cosine phi? Cosine phi in terms of the length is equal to cosine phi, if you remember, phi there, this is x and this is a. Cosine phi is equal to the adjacent x over a. So muna siyang x over a dira. And the a's here cancels out, and you are left with this one. Ax is equal to negative omega squared x. So going back, so ax is also an expression of the second derivative of the position is equal to negative kmx. Okay, substituting this one, same acceleration here is negative omega squared x is equal to negative k over mx. So the x's cancels out, the negative cancels out, so omega squared is equal to k over m. Taking the square root of both sides, and we get the angular frequency is the square root of k over m. Now let's look at an example here. You have a spring mounted horizontally with its left end held stationary. By attaching a spring balance to the free end, if we pull the right end with a force of 6 newtons, causes a displacement of 0.03 meters. We remove the spring balance and attach a 0.5 kilogram body to the end, pulling it to a distance of 0.02 meters, release it and watch it oscillates. Find the force constant when the balance is x equal to 0.03. So this is k, find the force constant. And find the angular frequency, and the period. Let's go. So first step, we draw the problem. So we pull it by a spring balance, let's say this one, and case B, pulled by a mass, this one here. So they have Fx as a restoring force. Okay. The letter A, find the force constant of the spring balance when x is equal to 0.03. So we recall the expression for the restoring force, Fx is equal to negative kx. This is for a spring problem. K man ang gipangita, we rewrite that one as k is equal to negative Fx over x. So we know that ang force, restoring force niya is 6 newtons. So 6 newtons divided by 0.03 m. The negative here cancels out. Okay. So K is equal to 200 newtons. Letter B, find the angular frequency, the frequency, and the period. We recall the expression for the omega is equal to the square root of km. So we use this because na-solve naman nato ni. And we also know the mass. Substituting gives you the angular frequency or velocity, 20 radians per second. And for the frequency, we recall the expression 2 pi f. So f is equal to omega over 2 pi, which is 20 radians per second, solved earlier, divided by 2 pi. So that's frequency is 3.2 hertz. And we take the inverse of this one, then you arrive to the expression for the period 0.31 seconds. Now let's talk about displacement, velocity, and acceleration functions. Okay, in this case, you have the object is now moving from T naught to T. T naught, you have the angle given as phi, and as it moves, ang angle ni mo ni increase to some angle here. So the angle from with respect to the x-axis is theta, but we know this one is given as phi plus this change na angle. So x is equal to a cosine phi describes the position at the point p. So at the point p, that is x there. Technically, this is x naught at any time. P at any time. Not really. It's just P at this time. At T naught is equal to 0, the phasor nimo na OQ makes an angle phi with a positive x-axis. Then at a later time T, this angle is changed to theta, where theta is equal to phi plus this change here, omega t. Then x naught is equal to a cosine phi at time T naught, and x is equal to a cosine omega t plus phi at a later time t. Okay, it's the change in displacement. Okay, we can also write this in terms of the sine function. We simply use the identity cosine alpha is equal to sine alpha plus pi over 2, and the expression for the x, which is a cosine omega t plus phi. So by doing that, alpha is represented by this, so we just add plus 1. The value of the cosine function is always between -1 and 1. So x is always between -1, the amplitude negative a, and 1 is the positive amplitude a. Here we have this figure relating this behavior sa imong cyclic na motion o rotational, and you have the linear na behavior. And if you look at this way, as it moves through time, it shows a sine or a cosine function as it oscillates ang shadow niya. Okay, so let's dissect this. So if we look at let's say na diri ang mass nimo ha, na ang shadow niya is somewhere here sa linear, somewhere here pod ang imuhang shadow sa sine this is a cosine function, I believe. Yeah, indeed, it's a cosine function. So this is if it is allowed to move from position here to position here, it gives you a complete cycle. So this is the period niya. So that means this is half a period, okay? And A here would be the maximum displacement, the positive and the negative na displacement. So this now is, of course, relates why it is a cosine function, which can also be used which can also be translated into a sine function. Okay, so visually we can see that yes, repeating motion gives you a sine or a cosine function. So complete cycle and displacement relationship. So we know this one to be the whole period. So for one cycle, ang time t is one period, which we said. Then omega t is equal to omega times the period. And we recall earlier that the angular frequency is given as square root of k over m, and substitute putting it here. So omega t is equal to the square root of k over m. Nice ayup. Sorry, may labot natin. It's not going inside the square root. Then one cycle would result to a displacement of 2 pi, of course. Then omega t, which is basically the velocity times time, should give you a distance, which is equal to the period to the length 2 pi. So the period can be written as 2 pi over angular frequency. For this case, we simply invert this one. So period is equal to the square root of m over k. Okay. Now we solve for the velocity. For the velocity in the simple harmonic motion, we simply recall the expression for the velocity, which is the first derivative of the position x over dt. So the position x, if you remember, is, of course you should remember, kay bago lang, is a cosine omega t plus v. Taking the derivative with respect to time, dx over dt gives you, factor out ang omega here. Of course, derivative of cosine gives you a negative sign, and you keep then you derive this one, omega t plus v. So the v gives you 0. Omega t gives you omega. This is the expression for the velocity for simple harmonic. For acceleration, you take again the derivative of x the second time, or the first derivative of the velocity, dv over dt. So you have, we keep this, you factor out this one, and derivative of a sine is a cosine function. Is this not? Yeah, it's a sine omega t plus. Okay. Oh yeah, derivative of a sine. I think napa siya negative here. Yeah, should be negative there. So derivative of sine is a cosine omega t plus phi. So na kay x and omega, this becomes omega squared. And omega squared, if you remember, omega squared is, or omega is the square root of k over m. So square root of that one gives you this. Substituting, you can express it. Okay. Given the initial position x naught and initial velocity v naught for the oscillating body, determine the phase angle phi and the amplitude a at time t naught 0. So the first step is we use this expression. Recall that x naught and v naught at time t naught is given by the following expression. X naught is a cosine phi and v naught is equal to negative omega a sine phi. You take the ratio because our goal is to simplify the function. So we have v naught over x naught, so that we can get a tangent phi from the relationship with this one. Of course, the amplitude cancels out. So what do we get? So this is basically v naught x naught is equal to negative omega tangent phi naught. And of course, we transpose this on here. You get this term negative v naught over omega x naught. When you take the tangent inverse, and you get an expression for the phase angle phi at time t naught 0. Next is solving for the amplitude. The amplitude, what do? We use the same expression, pero we square ang x naught squared and v naught squared. So this becomes a squared cosine phi squared v naught squared omega. Why? We want an expression na sine squared and cosine squared, so that we can use this identity. So cosine phi squared is just x naught squared over a squared. Substitute here. Then sine phi squared is just v naught squared over omega squared a, and it is equated to a. And what do? We factor out 1 over a squared, we cross it, and we arrive to this expression here. This is the amplitude at time t naught 0. Now, let's look at the effects of changing parameters to sinusoidal wave na function. So this is the position x at time t for a cosine function. Remember, kung sine na siya na ay plus pi over 2, right? So, and omega is this one, and t. If we increase the mass, while the amplitude and the constant k are constant, it would happen like there's an increase in the period, longer ang one complete cycle ni. If increase ni mo mass, okay, increasing the mass increases the period, so they're almost like proportional behavior. Here we increase the spring constant, while a and m are constant, increasing the spring constant. So this is what happens sa period niya for T1. What happens if magkadako ang value sa spring constant, ang period magkagamay, because if you look at here, nasa ubos, the period is inversely proportional sa imong spring constant. Increase ang iyang period. Last is increasing the amplitude. So the amplitude. So here, if we increase the amplitude, what happens to this function here? Actually, the period remains the same. It's not really affected. But amplitude lang nag-increase niya. See, wala siya correlation. Now, of course, talk about the energy in simple harmonic. So again, the mechanical energy is the sum of the kinetic and the potential. So here, the potential here is the potential energy due to its elastic potential siya. So you have two scenarios. The first scenario is ang spring is being compressed by the mass while it is moving. So naakay potential sa spring o naakay kinetic energy sa block of mass. At this point here, the second case that na-reach niya ang maximum amplitude, so ang velocity mo 0. So mabili na lang isang elastic potential due to the spring. So that's your E1 and E2 for this case. Now, if we compare, so ang imuhang E1, the mechanical energy equated to E2 equal to 0, conserve man siya. So 1 half mv squared plus 1 half kx squared is equal to 1 half kx squared. So let's recall some function here. Ang x ni mo position niya is a cosine omega t plus phi. Ang v ni mo is negative omega a sine omega t plus phi. Let's substitute. So from here, ang v squared ni mo, you take the v squared of this one. You have this one here. So mawala ang negative na sign. It simply becomes omega squared a squared sine omega t plus phi quantity squared. Ang x ni mo, which is a cosine omega t plus phi, gives you this a squared cosine omega t plus phi. So we recall two equations here. One is identical. Omega is equal to the square root of km. So omega squared gives you this function here, k over m. So the masses cancels out. The second one is ang kaning identity na cosine squared phi plus sine squared phi gives you an identity na 1. Gives you a value of 1. So if this is sine squared, this is cosine squared. So the sum, if you have the same terms, if we're able to reach the same terms, it's simply equal to 1. Let's see if we can do that. So here we already cancel out, so this becomes ka squared. This one is already ka squared. Now since this one, sine squared phi, cosine squared phi, they have the same quantities nila, same variables na sila, simply becomes 1. 1 na lang siya. 1 times a squared k times 1. So the energy is equal to 1 half k squared, which is a constant. Okay. So indeed, kanisha is result to this one. Okay, let's look at the velocity of the simple harmonic motion and the velocity maximum. Of course, the maximum wouldn't be here at the very edge. Okay, stop naman siya mo 0. Ang maximum niya would be at the equilibrium ang yung velocity. So we recall the total mechanical energy, which is 1 half mv squared plus 1 half kx squared is equal to 1 half k squared. Okay, let's try to write an expression for the velocity. So that means this one is transposed side. So this becomes a squared. Then they have difference kanisha. A squared or x squared. So this becomes a squared minus x squared. The 1 halves will cancel out. And you throw, you cross the mass here. So this becomes k over m. Then to solve for the velocity, we take the square root of both sides. So we have plus minus square root of km. Square root of a squared minus x squared. Okay, so this is the velocity. This is the velocity na function. Now the maximum velocity is when x is equal to 0. So when x is equal to 0, the equation is reduced to this. Okay, square root of k over m times the amplitude. This is the maximum value of the velocity. This is at the positions of equilibrium. You also recall that this can be simplified as omega. So plus minus omega times the amplitude. Now let's look at application of simple harmonic motion. So this time it's a vertical. Initially, ang spring na siya length L. Once we attach a mass here, mas stretch siya gayo. Mas stretch siya because of the force sa weight. Huwag na siya restoring force na equal to K delta L. Delta L is just the length minus the original, the length na pagka-stretch minus L. Or x is equal to delta L. So the restoring force here is again negative kx. K is kept, and if the force is kanang nakay pasaka, ang weight ni paubos, you have this function here. Okay, that would be the restoring force. Next, that would be I think that would be the net force. Next one is pag drop niya mo bounce man siya gamay, so you have this event here. K is equal to K, still have the spring constant, pero what happens is that na siya movement gamay ni saka siya. You still have the weight, pero na kay ni-act na ang restoring force trying to pull it back. So the x here, fkx, ang x nimo here would be delta L minus y. So you still have the restoring force, but this time ang x nimo is delta. So the net force nimo is k times x, which is delta L minus y, minus the weight, which is mg. Ano ang difference nila? Okay. So the F net Y is equal to F restoring minus weight is equal to minus Kx. Okay. Then expressing it, ang restoring force is K delta L minus Y is minus mg is equal to negative Kx. The vertical simple harmonic motion doesn't differ from the horizontal. The difference is that the position x no longer corresponds to the point at which the spring is unstretched. Okay, let's look at some example to help. You have a shock absorber in an old car with a mass 1,000 kilograms are completely worn out. When a 980 newtons person climbs into a car, it sinks around 2.8 times 10 to the minus 2 meter. The car with a person aboard hits a bump. The car starts to oscillate ups and downs. So find the period and frequency. Of course, sign na frequency relationship niya sa period. But, let's go. So this is unoscillated niya. Huh? So y is equal to 0. So no vibration. Now, once it is vibrating, naguna ng person na naka-weight sa person added sa weight sa car. So of course, na siya compression na length which is given. Okay? And of course, na siya restoring force. Same as gyapon with this one. Okay? Naman kay weight sa car here, put siya restoring force. Okay? The weight of the person creates a compression length x. So minus kx ang weight sa person. So k can be written as negative weight sa person over x. Take note kung wala pa siya weight sa person, wala pa kay x dira. So it's at y equal to 0 or 0 pa siya. So k gives you this value of 3.5. Okay? We recall the expression sa imong period which is 2 pi m over k. But m here refers to the mass total, the mass of the car plus mass of the person. So m total is equal to this value here. Ang weight of person is kuan naman 980 newtons divided by 9.8 is 100 kilograms. So it's 1,000 kilograms plus 100 kilograms divided by the k, the spring constant. 3.5 times 10 to the 4 kilo. And this gives you a period of 1.11 seconds. Frequency of 0.91 seconds using the inverse relationship. Okay, diba? Quite easy. Now, we have here a body of mass 0.5 kilogram is attached to a wall by a spring constant of 100 newtons per meter. It is given an initial velocity at x naught or x equal to 0 or 5 meter per second. Letter A, find the total energy of the body. Letter B, find the amplitude of oscillation. Letter C, find the velocity when the displacement is half the amplitude. Letter D, find the displacement when the velocity is half the initial velocity. Letter C, find the displacement when the kinetic potential energy are the same. Letter F, find the frequency and the period of the motion. And letter G, find the maximum acceleration of the body. So here we have a figure na naka-explain, naka-spring constant 100 meter at equilibrium na siya initial velocity na 5 meter per second. So letter A, find the total energy of the body, which is simply the sum of the kinetic plus the elastic potential. So nasa sa equilibrium position x0, so that is 0 there. So you are simply looking at the total energy as the kinetic energy, which is mass times velocity squared, which is 6.25 joules. Okay. Next is find the amplitude of the oscillation. This happens, ang amplitude makita rin mo if nasa sa maximum. Okay, at equilibrium, wala na, x equal to 0 man. And maximum lang siya if ang velocity niya at that point is 0. So meaning, we look at the energy function again, which we already know na siya sum na 6.25 Newton meter. But this time, nasa sa, kung pa, nasa here. Okay? Nasa here. Nasa kaniyang spring. The velocity here is 0. Okay? And this is the x equal to a maximum number. Okay? So that means 0 ang velocity, ni-stop na siya. Ang nabili na lang is spring, plastic potential energy sa spring. Rewriting that one, 1/2 Ka is equal to Ka squared, 6.25. And simplifying, we cross this one to here. And taking the amplitude. Yeah. So solving for the amplitude gives you this function here is around 0.35 meters. Letter C, find the velocity when the displacement is half its amplitude. So when x is equal to 1 half. At that point, kung x is equal to 1 half, kung let's say mo ni siya ang equilibrium wherein x is 0, and here is the x at maximum, pero v is 0, so now somewhere here, ang half sa amplitude, and it has both kinetic and potential na elastic. So we simply substitute a over 2 here, half naman. So what we do, solving an expression for v gives you this function here, substituting ang value sa maximum amplitude a and the mass ni mo gives you a velocity plus minus 4.03 meter per second. Next is find the displacement when the velocity is half the initial velocity. So again, the initial velocity is 5 meter per second. You have that one. So the expression is napaman siya x gihapon dira. So nakay elastic potential energy and kinetic energy. And rewriting to solve for x kay displacement man ang gipangita. So writing this one, you arrive to this expression here. Substituting the values, so x is around plus or minus 0.31 meters. Letter E, find the displacement when the kinetic and potential energy are the same. So when the kinetic and potential energy are the same, you have this expression ni mo So displacement gyapon x is equal to mv. This becomes mv squared over k. Substituting the mass, the velocity initial, and divided by k, the spin constant, x gives you this. And F, find the frequency and period of the motion. Okay, so the frequency, remember, can be solved using this expression here. 1 over 2 pi times the square root of km. Okay, take note, this one is also omega. Okay, so F, substituting the values, gives you the frequency. And the period is just 1 over F, 0.44 seconds. Okay, letter G, find the maximum acceleration of the body. So recall ax is equal to d squared theta, second derivative of theta with respect to t, is equal to negative k over mx. So maximum acceleration would be at x equal to a with v 0. So then a max is equal to negative k m times a. Okay, pulian na nato siya. Substituting a from the problem problem B, a is plus minus 0.35. So the maximum acceleration, if you substitute this one here and plug in this one, the k and the mass m gives you plus or minus 70 meter per second squared ang imuhang maximum acceleration. And that's it. So I hope you learned something new today, and God bless and ingat. Bye.